The surface of the ocean moves with rhythm. Waves rise and fall. Light breaks through the water in rays that shimmer and fade. Everything you see is familiar, measured, knowable. But that familiarity is a kind of blindness. Beneath the visible world is another realm entirely. Not another ocean, but the same ocean transformed. There are places where the sea does not meet the sky, where a roof of ice stretches between water and air, where darkness settles so completely that your eyes forget how to see. The water beneath is cold, not the cold of winter mornings, but a cold that reaches through steel and glass, a cold that moves through everything. This frozen ceiling extends farther than countries. It drifts above an ocean deeper than mountains are tall. Some ice shelves cover areas larger than entire nations. The thickness varies. In some places, hundreds of meters of ice press down upon the sea. In others, the barrier thins to fragile sheets. Beneath this roof, the ocean holds more water than all the rivers on Earth combined. The space is vast enough to contain mountain ranges, deep enough to swallow cities whole. Distance here is measured differently. A kilometer feels like 10. An hour stretches into something longer. Under the ice, familiar rules begin to fail. Light does not penetrate. Sound moves strangely through layered water. Temperature creates boundaries you cannot see but cannot cross. The surface above does not stay still. It moves. It breathes. It changes shape while you drift below. What seems solid is actually flowing. What appears stable shifts without warning. The ice responds to forces that work across decades and centuries. Below, the water holds memories older than human history. It carries signatures from distant seas. It flows in patterns that were set in motion long before anyone thought to measure them. Here, understanding becomes uncertain. Questions multiply. Answers drift away. This is a journey into a world that exists between states, neither fully frozen nor entirely liquid. A boundary where two elements meet and create something neither expected. There are creatures here that have never seen sunlight, waters that have not touched the atmosphere in thousands of years, landscapes carved by pressure and time into shapes that defy easy description. The ice above guards this world. The darkness preserves it. The cold sustains it. What follows is a descent through distance and depth, a movement away from the familiar surface, into a realm where the ocean remembers what it was before anything named it. Welcome to Info Jungle. If you enjoy calm, thoughtful documentaries about the natural world, consider subscribing. These videos are created to help you relax while learning at a gentle pace. Antarctica holds most of the fresh water on Earth. It sits at the bottom of the world as a continent wrapped in ice. The ice sheet covering it is ancient and immense. But the ice does not stop at the shoreline. In many places, the sheet continues outward. It extends over the ocean in platforms called ice shelves. These shelves float on seawater while remaining attached to the land. The edge where ice meets ocean is not a simple line. The ice above can be hundreds of meters thick. It presses down with enormous weight. Yet it floats. This seems impossible until you remember that ice is less dense than water. The shelf rides on the ocean like an enormous raft. Most of its mass sits below the surface. What you see from above is only a fraction of the whole. Between the bottom of the ice shelf and the seafloor lies a cavity. This space varies tremendously. In some locations, the gap measures only a few meters. In others, it opens into chambers hundreds of meters tall. The cavity is filled with seawater. Cold seawater, dark seawater. The ice above acts as a ceiling that nothing can penetrate. No sunlight reaches through. No storms disturb the surface. No wind touches the water below. This creates an environment unlike any other on the planet. The ocean here exists in a state of profound isolation. Cut off from the atmosphere, separated from the rest of the sea by barriers of ice and distance. The water beneath ice shelves hovers near the freezing point. But it does not freeze. Seawater freezes at a lower temperature than fresh water. The salt keeps it liquid even in extreme cold. The temperature stays around -2 degrees Celsius. At this temperature, most life would cease. Most processes would slow to nothing. But the ocean beneath the ice is not still. Pressure plays a role here as well. The deeper the water, the greater the weight pressing down from above. This pressure lowers the freezing point even further. In the deepest cavities, water can remain liquid at temperatures that would turn fresh water solid. The combination creates a delicate balance. The ice does not grow downward indefinitely. The ocean does not freeze solid. They exist in equilibrium. The cavity is not a sealed chamber. Water flows in and out. Currents move through the darkness beneath the shelf. Warmer water from the open ocean finds pathways inward. It travels along the seafloor and rises toward the ice above. As it rises, it carries heat. This heat melts the ice from below. The melting is slow, sometimes only centimeters per year, sometimes more. The meltwater is fresh. It is less dense than the salty seawater around it, so it rises along the underside of the ice shelf. It forms a thin layer between ice and ocean. This layer flows outward. It travels toward the edge of the shelf, where it eventually mixes with the open sea. The circulation creates a constant exchange. Water enters. Water leaves. The cavity breathes. There is a place where the ice shelf touches the seafloor. This boundary is called the grounding line. Landward from this line, the ice rests on solid ground. Seaward from it, the ice floats. The grounding line is not fixed. It can migrate over time. If the ice shelf thins, the grounding line retreats inland. If the shelf thickens, the line advances toward the ocean. This boundary is critical. It determines how much ice flows from the continent into the sea. It influences the stability of the entire ice sheet. Near the grounding line, the cavity is often very thin. The ice presses close to the seafloor. Water must flow through narrow gaps. The pressure is immense. Farther from the grounding line, the cavity opens. The ice lifts away from the bottom. Space expands. The bottom surface of an ice shelf is not smooth. It has texture and shape. In some places, channels carve through the ice from below. These channels form where meltwater flows preferentially along certain paths. They can be tens of meters deep. They run for kilometers. In other places, the ice forms ridges and bumps. These features create a landscape on the ceiling of the cavity, a topography turned upside down. The ice also contains layers. Each layer represents snow that fell on the surface years or decades ago. The snow compressed into ice over time. The layers record the history of accumulation. Near the bottom, the ice can contain marine ice. This is ice that formed from seawater freezing onto the shelf from below. It has different properties than the ice that formed from snow. Its crystals are arranged differently. Its chemistry carries the signature of the ocean. Even in this cold and dark environment, life exists. Near the ice ceiling, small organisms cling to the frozen surface. They are invisible to the eye without magnification. But they are there. Bacteria survive in thin films of liquid water between ice crystals. They metabolize slowly. They use chemical energy instead of sunlight. In the water column, tiny crustaceans drift. They are translucent. Their bodies move with subtle contractions. Fish appear occasionally. They are specially adapted to the cold. Their blood contains antifreeze proteins. These proteins prevent ice crystals from forming inside their cells. The fish move slowly. They conserve energy. Food is scarce. Every calorie matters. Beneath the ice and water lies the seafloor. In many places, this is the continental shelf. The continental shelf is the submerged edge of the continent. It slopes gently downward from the coast. Eventually, it drops off more steeply into the deep ocean. The shelf is covered in sediments. These sediments were deposited over millions of years. Some came from rivers that once flowed when Antarctica was warmer. Some came from glaciers grinding rock into fine powder. The sediments hold their own secrets. They contain layers that record past climates. They preserve the remains of organisms that lived long ago. They show how the ice sheet has advanced and retreated through time. Even beneath the ice, the ocean responds to seasons. In summer, the ice shelf experiences more melting. The increased meltwater changes the properties of the water beneath. The fresh water layer grows thicker. Circulation patterns shift. In winter, melting slows. The water becomes more homogeneous. Temperatures stabilize at their lowest point. These seasonal cycles are subtle. The ice provides insulation from the dramatic changes happening on the surface. But they are detectable. Organisms beneath the ice may respond to these cycles. Some species become more active during certain months. Others show no seasonal pattern at all. They exist in a perpetual state, adjusted to constant cold and darkness. The cavity beneath an ice shelf is not completely isolated. At the ice front where the shelf ends, the cavity opens to the sea. Here, water exchanges with the surrounding ocean. Currents flow in and out. Nutrients enter. Organisms migrate. This connection is vital. Without it, the cavity would become stagnant. Oxygen would be consumed. Life would struggle to persist. The ice front is also where icebergs are born. Large pieces of the shelf break away in a process called calving. These bergs drift into the ocean. They carry pieces of the ice shelf with them. Scientists study ice shelves using various methods. They drill through the ice to access the water below. They lower instruments through the drill holes. They collect samples and make measurements. These expeditions are challenging. The ice is thick. Drilling takes days or weeks. The equipment must operate in extreme cold. Sometimes they deploy underwater vehicles. These robots swim through the cavity. They carry cameras and sensors. They map the underside of the ice. They photograph the seafloor. Each expedition adds to our understanding. Each measurement refines the picture. But vast areas remain unexplored. The ice shelves of Antarctica cover more than 1.5 million square kilometers. humans have directly sampled only a tiny fraction of that area. The cavity beneath an ice shelf presents problems that have no surface equivalent. You cannot see the ceiling above you. You cannot see the floor below. Distance becomes a guess filtered through instruments that may or may not be accurate. Navigation requires trust in tools, but the tools themselves struggle here. Compasses waver near the magnetic pole. GPS signals cannot penetrate ice. Sonar returns echoes that seem contradictory. An object appears close but is far. A clear path shows obstacles. The map drawn by instruments does not match the space they occupy. This is not malfunction. This is the nature of the environment. The water beneath ice shelves carries distinct chemical properties. It contains oxygen. This oxygen came from the surface long ago, when the water was last in contact with air. As time passes, organisms consume the oxygen. The levels drop slowly. The water also contains nutrients. Nitrogen and phosphorus dissolved in the seawater. These nutrients support the microorganisms that form the base of the food web. Iron is present as well. It comes from the seafloor below. Rocks release iron slowly into the water. This iron is essential for many forms of life. Scientists can measure these chemical signatures. They tell stories about how long the water has been isolated, about how much melting has occurred, about the balance between life and decay. Sound behaves differently under ice shelves. In the open ocean, sound waves travel freely. They spread out in all directions. They reflect from the surface and the bottom. Beneath an ice shelf, the geometry changes. The ice above acts as a reflector. Sound bounces between the ice ceiling and the seafloor. It becomes trapped in the cavity. This creates unusual acoustic environments. Sound can travel farther than expected. Echoes persist longer. The cavity acts like a waveguide. Scientists use sound to study these environments. They send pulses through the water and listen for returns. The echoes reveal the shape of the cavity, the thickness of the ice, the depth of the water. But sound also reveals movement. The melting of ice creates tiny bubbles. These bubbles make noise as they form and rise. The noise is faint but measurable. Water beneath ice shelves arranges itself into layers. These layers differ by fractions of a degree, by small variations in salt content. The boundaries between layers are invisible. You cannot see them. You cannot feel them if you were somehow present in the water. But they are real. A layer of slightly warmer water may sit above a layer of colder water. The warm layer came from deeper in the ocean. It traveled hundreds of kilometers to reach this place. The layers do not mix easily. They slide past one another. They maintain separation for months or years. Sound bends when it crosses these boundaries. Light would bend too if light were present. The cavity becomes a lens made of water. Instruments aimed at the seafloor may find their signals curving upward. Sensors looking for the ice above may detect reflections from the side. The data collected is accurate. The interpretation becomes difficult. In the open ocean, you develop a sense of proportion. A whale is large. A ship is visible. Distance can be judged by how objects fade into blue haze. Beneath the ice shelf, these references vanish. The cavity can be 10 meters tall or 300. The ice shelf can be 1 kilometer wide or 50. Without light to show perspective, the mind cannot anchor itself. A scientist lowering an instrument through a drill hole cannot see what waits below. The instrument descends on a cable. 100 meters. 200. 300. Is it near the bottom? Is it halfway? The answer comes only when the sensor strikes something or the cable runs out. Submarines navigating these spaces report similar disorientation. The sonar shows walls and ceiling and floor, but the relationships between them feel wrong. Distances seem compressed or expanded. The human brain expects certain patterns. It expects up and down to remain constant. It expects distance to correlate with time and effort. Here, those expectations fail. Water pressure increases with depth. This is constant, predictable. But beneath ice shelves, pressure also varies horizontally. The weight of the ice above creates zones of higher pressure directly beneath the thickest sections. Where the ice thins, the pressure drops. Water flows from high pressure to low pressure. This drives circulation in unexpected directions. A current may flow upward and sideways simultaneously. Water near the grounding line experiences pressure from multiple sources. The weight of ice, the depth of water, the force of incoming currents. These pressure zones influence everything. They determine where ice melts fastest. They guide the path of organisms. They shape the cavity itself over time. Understanding pressure here requires thinking in 3 dimensions. Not just depth, but horizontal variation. Not just at one moment, but changing across seasons and years. The underside of the ice shelf contains channels. These are carved by flowing meltwater. The channels can be enormous. Some are 50 meters deep. Some extend for 20 kilometers or more. They form where warm water preferentially melts the ice. The melting creates a groove. The groove channels more water. More water brings more heat. The channel deepens. Over time, the channels create a network, a drainage system carved into the ceiling. But the channels do not stay in one place. The ice shelf moves. It flows toward the ocean at rates of hundreds of meters per year. The channels move with the ice. They drift above the seafloor like slow rivers in the sky. This creates a puzzle. Where is the channel now? Where will it be next year? Maps become outdated before they are completed. The place where ice begins to float is not fixed. If the ice shelf thins, the grounding line retreats. The ice lifts away from more seafloor. The cavity expands inland. If warm water reaches the grounding line, melting accelerates. The retreat can become rapid. This retreat is not uniform. One section of the grounding line may move, while another remains stable. The boundary becomes irregular. It forms peninsulas and embayments. Scientists trying to map the grounding line face challenges. The boundary exists beneath hundreds of meters of ice. It cannot be seen. It must be inferred from surface measurements and indirect observations. Satellites detect subtle changes in ice elevation. These changes hint at where the ice has begun to float. But the precision is limited. The grounding line moves faster than it can be accurately mapped. Ice shelves melt from below. The rate varies. In some locations, the ice loses only a few centimeters per year. In others, melting exceeds 10 meters per year. The difference depends on water temperature, on circulation patterns, on the shape of the cavity. A cavity with restricted circulation experiences less melting. The water near the ice cools as it melts the ice. The cold water becomes less effective at further melting. A cavity with strong circulation constantly brings new warm water. The melting never slows. Predicting melt rates requires understanding the full system. Ocean currents far from the ice shelf. Winds on the surface. Seafloor topography. The thickness and shape of the ice. Change one variable, and the melt rate changes. The relationships are nonlinear. Small changes can have large effects. Life beneath ice shelves exists in conditions that allow no mistakes. Organisms cannot rely on backup systems. They cannot migrate to better conditions. The cavity is their entire world. Fish here possess proteins that prevent freezing. But the proteins have costs. They require energy to produce. They change how cells function. In warmer water, these fish would be at a disadvantage. Their modified biology would be unnecessary overhead. But in this environment, they survive where others cannot. The bacteria living here metabolize at rates barely measurable. They divide perhaps once per month. They exist in a state between life and dormancy. Yet they persist. They have persisted for thousands of years. The question is not whether they can adapt. They have already adapted. The question is whether they can adapt again. If conditions change faster than their generation time, adaptation may be impossible. The water beneath ice shelves is not in equilibrium with the atmosphere. Oxygen levels may be lower or higher than expected. Carbon dioxide concentrations differ from the open ocean. Trace metals appear in unusual ratios. This disequilibrium provides information. It shows how isolated the water has been. How long since it last mixed with the surface. Some water beneath ice shelves has not contacted the atmosphere in decades. Some in centuries. The chemical signatures record this isolation. They become clocks. But interpreting these clocks is complex. Multiple processes affect the chemistry. Melting adds fresh water. Organisms consume nutrients. Sediments release or absorb compounds. Scientists must account for all these factors. They must separate the signal from the noise. Often, the noise is louder than the signal. The movement of water beneath ice shelves does not follow simple patterns. In some places, the flow is steady and predictable. In others, it pulses. Periods of strong flow alternate with near stagnation. These pulses may be driven by tides. Even beneath the ice, the ocean rises and falls slightly. The pressure changes. Water accelerates or slows. The flow can also be influenced by processes far away. A storm in the open ocean creates pressure waves. These waves propagate for thousands of kilometers. They reach beneath the ice shelf. They perturb the currents. The cavity responds to these distant events. It connects to the larger ocean, even while remaining physically separate. Understanding this connection requires measurements taken over long periods. Days are not enough. Weeks reveal only fragments of the pattern. Months or years begin to show the full picture. But months or years of continuous measurement beneath an ice shelf are difficult to achieve. Instruments fail. Batteries drain. Ice closes drill holes. The data remains incomplete. The seafloor beneath ice shelves holds layers of sediment. These layers accumulated over millennia. They should be undisturbed. protected by the ice above, isolated from storms and currents that churn the open ocean floor. But they are not entirely undisturbed. Currents along the bottom can be strong enough to move fine particles. Organisms burrow through the sediment. Meltwater raining down from the ice stirs the surface layers. In some places, the sediment shows signs of recent disturbance. Layers are mixed. The stratigraphy is unclear. This makes interpretation difficult. The sediment should be a record of the past. But if the layers are mixed, the record becomes illegible. Scientists must determine whether disturbance is ongoing or past, whether it is natural or influenced by recent changes. The answers are not always clear. At the ice front, pieces of the shelf break away. This calving process creates icebergs. Some are small. Some are enormous, the size of small countries. The calving is episodic. Years may pass with little activity. Then a major event occurs. A large section detaches and drifts away. What triggers calving is not fully understood. Cracks propagate through the ice. They grow slowly, then suddenly accelerate. The ice separates along these cracks. The new berg pivots and floats away. For the cavity behind, this creates a sudden opening. The protected space becomes exposed to the open ocean. Water properties change rapidly. Circulation patterns shift. Organisms that adapted to the sheltered environment must now cope with new conditions. Light may reach places that were dark for centuries. Warmer water may flood in. The calving of a large iceberg reshapes the entire system. Nothing beneath the ice remains static. Melt rates change seasonally. Currents strengthen and weaken. The grounding line advances or retreats. But these changes occur on timescale that make observation difficult. A measurement taken today shows one state. A measurement taken next year shows a different state. But was the change gradual or sudden? Did it occur steadily throughout the year or in a brief pulse? Without continuous monitoring, these questions cannot be answered. Scientists piece together the story from scattered observations. They infer processes from snapshots. They build models to fill the gaps. The models may be accurate. They may be wrong. The uncertainty remains. Studying ice shelf cavities requires remote instruments. These instruments collect data, but transmitting the data is difficult. Radio signals do not penetrate ice or water. Acoustic signals travel slowly and carry limited information. Most instruments must store data internally. They record for months. Then they must be recovered. Only then can the data be analyzed. This delay is frustrating. If an instrument malfunctions, the problem is not discovered until recovery. Months of data may be lost. If an unexpected event occurs, it cannot be observed in real time. Scientists learn about it only later. They cannot adjust their measurements. They cannot deploy additional sensors. The cavity remains opaque until the instrument returns. Large sections of ice shelf cavities have never been sampled. The logistics are too difficult. The risks too high. The cost too great. Scientists must choose where to focus limited resources. They target areas that seem most important, most likely to reveal useful information. But this creates bias. The unstudied areas may contain surprises, unexpected features, unusual organisms, processes not seen elsewhere. The picture remains incomplete. The gaps in knowledge are larger than the knowledge itself. This is the nature of exploration here. Every answer generates new questions. Every measurement reveals how much more remains unknown. There is a point where understanding breaks down entirely. Not because instruments malfunction or data is insufficient, but because the cavity exceeds the framework used to comprehend it. Models built on open ocean assumptions predict outcomes that do not occur. Variables thought to be independent prove to be coupled. Processes assumed to be linear show threshold behaviors. Scientists enter regions where prediction becomes guesswork, where confidence intervals expand to encompass nearly all possibilities. The cavity reveals itself to be fundamentally different, not just in degree but in kind. A system governed by rules that are still being discovered. This is not a failure of science. It is an encounter with something genuinely beyond current reach. The instruments used beneath ice shelves operate at the edge of their capabilities. Sensors designed for open ocean conditions perform differently here. Calibrations may drift in extreme cold. Readings may be affected by the unique water properties. Temperature sensors accurate to thousandths of a degree in the lab may have larger errors in the field. Salinity measurements may be affected by melting ice nearby. Scientists must estimate these uncertainties. They must determine which measurements are reliable. Sometimes contradictory readings appear. Two instruments in the same location give different values. Which is correct? There is no easy answer. Both may be wrong, or one may be measuring something the other is not. The uncertainty compounds when building a picture from multiple instruments. Each measurement has error bars. Combined measurements have larger error bars. The confidence in conclusions decreases. Measuring ice shelf thickness seems straightforward. Use radar to find the top surface. Use sonar to find the bottom surface. Subtract. But the bottom surface is not smooth. It has roughness at multiple scales. Small scale roughness, centimeters to meters. Medium scale roughness, tens to hundreds of meters. Large scale roughness, channels and ridges kilometers long. Which roughness scale matters depends on the question being asked. For understanding ice flow, large-scale features matter. For understanding melting, small-scale features matter. Measuring all scales simultaneously is impossible. Each requires different instruments with different resolutions. The thickness becomes not a single number, but a distribution. A range of values. A probability. Reaching the water beneath an ice shelf requires drilling through ice. The drilling may take weeks. The drill bit must remain hot enough to melt through ice, but not so hot that it damages itself. Drilling fluid must be chosen carefully. It must not contaminate the pristine water below. It must not freeze in the drill hole. As the hole deepens, the ice around it deforms. The pressure tries to close the hole. The drilling must proceed quickly enough to prevent closure. Once through, the hole provides access for only a limited time. Hours to days. Then the ice closes the hole again. All measurements must be completed in that window. All samples collected. All instruments deployed. There is no second chance. If the instrument becomes stuck, it is lost. If the cable breaks, the data is lost. If the hole closes prematurely, the mission fails. Every deployment is a gamble against time and ice. The ice shelf exerts pressure on everything beneath it. This pressure is not uniform. It varies with ice thickness. It changes as the ice moves. The pressure affects water properties. It affects how organisms function. It determines the melting point. But more than that, it creates a psychological weight. Scientists working above the ice shelf feel it. The knowledge that hundreds of meters of ice press down, that the ice could collapse, that the drill hole could close. The weight is always present, not physically felt, but known. Some features beneath ice shelves exist only temporarily. A current may create a small eddy. The eddy persists for days or weeks, then disappears. A pocket of warm water may become trapped. It slowly mixes away. It leaves no permanent trace. These ephemeral features are real. They affect organisms. They influence melting. But they are nearly impossible to study. By the time scientists detect them, they may be gone. By the time instruments are deployed, conditions have changed. The cavity contains processes that exist between measurements, events that occur in the gaps. The record is full of holes. Some changes beneath ice shelves cannot be undone. If the grounding line retreats past a certain point, the retreat may become unstable. The ice shelf may collapse. The cavity may cease to exist. If warm water reaches previously isolated regions, the ecosystem may be permanently altered. Species adapted to the cold may not survive. New species may invade. These changes are not experiments. There is no control group, no way to reverse the process. Scientists observe the changes as they happen. They document. They measure. They try to understand. But they cannot stop the changes. They can only watch. In the water column, amphipods drift with barely perceptible motion. Their bodies are translucent to the point of invisibility. Each leg moves in sequence, a slow rhythm that conserves what little energy is available. They feed on particles suspended in the water, fragments of organic matter that have sunk from distant places, pieces of algae that once grew at the ice edge, bacteria that release from melting ice. The amphipods do not hunt. They filter. They wait. Their metabolism operates at a fraction of what it would be in warmer seas. Cell division happens infrequently. Growth is measured in weeks or months for changes that would take days elsewhere. Reproduction occurs but slowly. Eggs develop over extended periods. Larvae emerge already adapted to the cold. There is no larval stage that requires different conditions. No migration to warmer waters. The entire life cycle happens here. In the dark. In the cold. In water that barely moves. The fish that inhabit these waters do not school. They drift alone, separated by distances that would make visual contact impossible, even if light existed. Their bodies are slender, their fins large relative to their mass. This configuration provides neutral buoyancy with minimal effort. They hang in the water column without swimming, without sinking. Their eyes are functional but underused. Vision here provides little advantage. Instead, they rely on lateral line systems. Sensors along their bodies detect pressure changes, vibrations in the water, the movement of other organisms. Prey is detected not by sight but by disturbance. When a fish strikes, the motion is economical. A brief acceleration, a snap of jaws, then stillness again. On the underside of the ice, bacteria form thin films. These films are not visible as distinct structures. They exist as molecular scale coatings. The bacteria attach themselves to the ice using proteins. They secrete adhesives that keep them in place, despite the slow flow of meltwater. Their metabolic processes are ancient. They do not use photosynthesis. Instead, they derive energy from chemical reactions, oxidizing sulfur compounds, reducing iron, breaking down organic molecules that diffuse through the water. The energy yield from these reactions is small, but the requirements are also small. The bacteria exist in a state of extreme efficiency. Every molecule metabolized, every electron transferred, nothing wasted. They reproduce by simple division. One cell becomes two, two become four, but the doubling time can exceed a month. In warmer environments, the same species might double in hours. Here, time itself seems stretched. On the seafloor, organisms anchor themselves to rocks and sediment. Sponges grow in forms that seem random. Their bodies filter water through countless pores. They extract microscopic particles, bacteria, organic fragments, dissolved nutrients crystallized into usable forms. The sponges grow slowly. A centimeter per decade is normal. Large specimens may be centuries old. Their tissues contain spicules made of silica. These glass-like structures provide support. They also record chemical signatures of the water over time. Scientists can core a sponge the way they core ice. Each layer represents a period of growth. Each layer contains information about past conditions. Nearby, sea stars move across the bottom. Their tube feet grip the sediment. They advance at rates measured in meters per day. Their motion is so slow it cannot be observed directly. Only time-lapse photography reveals their progress. They feed on other benthic organisms, occasionally on sponges, more often on smaller invertebrates buried in the sediment. Worms burrow through the seafloor. They ingest sediment and extract nutrition from the organic content. What they consume is not food in the conventional sense. It is sediment mixed with bacteria, decayed matter from organisms that died long ago. The nutritional value is minimal, but the worms process large volumes. They pass sediment through their gut continuously. The burrows they create aerate the sediment, allow water to penetrate deeper, facilitate chemical exchanges between layers. The worms themselves are rarely seen. They remain buried. Only their burrows mark their presence. Long tubes extending down through layers of mud and silt. Predation occurs, but at a pace difficult to reconcile with predation elsewhere. A sea spider stalks across the seafloor. Its legs span distances greater than its body. It moves with deliberation, each step carefully placed. It approaches a sea anemone anchored to a rock. The approach takes hours. The anemone does not flee. It cannot. It remains rooted in place. The sea spider extends its proboscis, pierces the anemone's tissue, begins to feed. The process takes days. The anemone does not resist in any visible way. It lacks the neural complexity for pain. It simply loses mass. Tissue is consumed. The anemone shrinks. Eventually, the sea spider moves on. The anemone may recover, or it may not. In certain locations, the seafloor releases chemicals. Volcanic activity below heats water. The water rises through cracks in the rock. It carries dissolved minerals, hydrogen sulfide, methane, iron compounds. Where this water emerges, bacteria gather. They use the chemicals as fuel. They oxidize hydrogen sulfide and release energy. This energy drives the synthesis of organic molecules. The bacteria do not need sunlight. They do not need oxygen from the atmosphere. They create the base of a food web independent of the surface world. Other organisms cluster around these seeps. Small crustaceans graze on bacterial mats. Fish come to feed on the grazers. The seeps create oases, pockets of higher productivity in an otherwise sparse environment. But the seeps are not permanent. The flow of chemicals can cease. The cracks can seal. The community collapses. Organisms disperse or die. The seafloor returns to its baseline state. Water movement beneath ice shelves is not constant. Currents accelerate and decelerate in response to forces both near and far. When currents strengthen, suspended particles move. Sediment on the seafloor is stirred. Organisms must adjust. Filter feeders orient themselves to maximize capture. Burrowing animals retreat deeper. Swimmers may move with the current or shelter behind obstacles. When currents weaken, particles settle. The water clears slightly. Visibility would improve if light existed. But in darkness, clarity makes little difference. The currents also transport nutrients. When flow increases, nutrient concentrations rise. When flow ceases, concentrations drop. Organisms respond to these fluctuations. Metabolic rates increase when food is more available. They decrease when resources become scarce. The cavity breathes in cycles. Not daily, not yearly, but in patterns linked to oceanic processes operating on longer timescales. The ice itself is not inert. Within the ice structure, microscopic pockets of liquid water exist. These pockets are smaller than the width of a hair. They form where salt or other impurities lower the freezing point locally. Inside these pockets, bacteria survive. They live within the ice. Their world is measured in micrometers. They cannot move. They cannot grow beyond the confines of their pocket. They metabolize at rates barely detectable. But they remain alive. When the ice melts, these bacteria are released. They enter the water column. They may resume more active life, or they may sink and become dormant again. The ice acts as both barrier and reservoir. It isolates life from the ocean, but it also preserves life within itself. No part of the cavity is truly isolated from the rest of the ocean. Water enters from outside. It brings with it traces of the world beyond. Larvae of organisms that live in open water. Organic particles from distant algal blooms. Chemical signatures of currents that began thousands of kilometers away. These arrivals introduce variability. They prevent the cavity from becoming entirely static. But the exchange is slow. Water may take months or years to circulate through the cavity and exit. During that time, it transforms. It cools. It loses oxygen. It gains meltwater. It becomes something different from what entered. By the time it leaves, it carries the signature of the ice shelf. It flows back into the ocean as a distinct water mass. Colder, fresher, denser in some regions, lighter in others. This water influences circulation patterns far from Antarctica. It sinks or rises depending on its properties. It joins currents that span ocean basins. The cavity is small compared to the global ocean, but its influence extends far beyond its physical boundaries. Organic matter in the cavity does not follow a simple path from producer to consumer. There are no producers here in the conventional sense. No photosynthesis. No primary production. Instead, organic matter arrives from elsewhere or is generated through chemosynthesis. Bacteria break down this matter. They release dissolved organic compounds. Other bacteria consume these compounds. They remineralize nutrients. The nutrients are taken up by different bacteria. The cycle continues. This microbial loop dominates the food web. Energy is transferred and retransferred through microbial metabolism. Only occasionally does energy move to larger organisms. A bacterium is consumed by a protozoan. The protozoan is eaten by a small crustacean. The crustacean becomes prey for a fish. But most energy cycles endlessly through microscopic life. It never reaches the macroscopic scale. The efficiency is low. Energy is lost at each transfer. But the system persists because input is continuous. Meltwater brings organic particles. Currents deliver nutrients. The microbial loop operates without interruption. The organisms here do not have options. They cannot leave if conditions worsen. They cannot migrate to better habitats. Their adaptations are not choices. They are constraints that allow survival in this specific place. A fish with antifreeze proteins cannot simply stop producing them. The proteins are coded in its genome. They are expressed regardless of conditions. If the water warmed, the fish would continue producing proteins it no longer needed. This would waste energy. It might become a disadvantage. But evolution does not prepare organisms for conditions they have never encountered. It only adapts them to the conditions they face. The fish are perfectly suited to water at -2 degrees. They would struggle at 0 degrees. They would likely die at 5 degrees. Their perfection is also their limitation. The seafloor beneath the ice is not static. Sediment accumulates grain by grain. Each particle settling from the water column adds to the layers below. The rate is slow. Millimeters per 1,000 years in some places. Centimeters in others. The sediment compresses under its own weight. Water is squeezed out. The lowest layers become denser. Eventually, they may lithify into rock. But this process takes millions of years. In human timescales, the seafloor appears unchanging. Yet it is always in motion. Always transforming. The sediment also records events. A layer of ash from a distant volcanic eruption. A concentration of iron from a period of increased hydrothermal activity. A band of organic-rich material from a time when currents brought more nutrients. These layers tell stories. But the stories are written in a language that requires careful interpretation. The ice shelf itself is an archive. Each layer of ice represents snowfall from a specific year. The snow fell on the surface. It compressed into ice. It flowed slowly toward the ocean. Within the ice, air bubbles are trapped. These bubbles contain atmosphere from the time the snow fell. They preserve the composition of the air, the concentration of carbon dioxide, the ratios of oxygen isotopes. Scientists can extract these bubbles. They can measure the gases inside. They can reconstruct past climates. But the archive is not permanent. The ice melts from below. The oldest layers are lost first. They dissolve into the ocean. Their information is gone. The archive is constantly being erased from the bottom up. What remains is only the most recent history. The cavity operates on multiple scales simultaneously. At the molecular scale, chemical reactions occur. Bacteria metabolize compounds. Proteins fold and unfold. At the microscopic scale, cells divide. Protozoans hunt bacteria. Larvae develop. At the scale of meters, currents flow. Fish swim. Sponges filter water. At the scale of kilometers, water masses circulate. Ice channels migrate. The grounding line shifts. Each scale influences the others. A change in ocean circulation affects nutrient delivery. Nutrient delivery affects bacterial growth. Bacterial growth affects oxygen consumption. Oxygen consumption affects fish survival. Fish survival affects predation pressure. Predation pressure affects benthic community structure. The system is interconnected. Cause and effect blur. Everything influences everything else. Darkness is not simply the absence of light. It is a defining condition. Organisms here did not lose their vision through disuse. Their ancestors may have had vision, but over generations in this environment, vision became irrelevant. Natural selection favored those who allocated resources elsewhere. The result is not blindness in the sense of a deficiency. It is optimization for an environment where light does not exist. Some organisms retain light-sensitive cells, but they do not form images. They detect only the presence or absence of light. This might allow them to avoid predators that produce bioluminescence, or to detect the rare flashes of light that occur when certain chemical reactions take place. But mostly, light sensitivity serves no purpose. The darkness is total, unbroken, permanent. The cavity changes slowly compared to the open ocean. Surface storms do not reach here. Temperature swings are dampened. Salinity varies, but within a narrow range. This stability is a resource. Organisms need not cope with rapid fluctuations. They can specialize. They can optimize for specific conditions. But stability is also fragility. If conditions do change, the organisms may not cope. Their specialization becomes a vulnerability. The isolation that protected them now traps them. In most marine environments, seasons drive cycles. Algal blooms in spring. Increased feeding in summer. Migration in autumn. Dormancy in winter. Beneath the ice shelf, these cycles are absent or muted. The darkness is constant. The cold is constant. Food availability varies slightly with current patterns. But there is no spring bloom. No summer abundance. Organisms here exist in perpetual winter. They do not anticipate change. They do not prepare for better times. They simply persist in the conditions that are. The constraints here do not merely affect individual survival. They shape entire lineages across geological time. Species that arrived in this environment thousands of years ago have diverged from their surface relatives, not through dramatic change, but through accumulated refinements. A slightly different enzyme, a modified protein structure, a shifted metabolic pathway. These modifications accumulated slowly, generation after generation. The organisms became more efficient at existing here, but also more dependent on these specific conditions. Reproduction in this environment follows patterns that reflect its constraints. Many organisms produce few offspring, but they invest heavily in each one. Eggs are large, rich in nutrients. The developing embryo has resources to survive without feeding immediately. Some species brood their young. The parent protects eggs until they hatch. This increases survival rates, but it limits the number of offspring. Other species release larvae, but the larvae are advanced, already resembling miniature adults. They require less time in the vulnerable larval stage. Reproductive cycles may occur annually, or they may span multiple years. In some species, individuals reproduce once and die. In others, individuals reproduce repeatedly across decades. The strategies vary, but all reflect the fundamental constraint. When an organism dies, its body does not vanish quickly. Decomposition proceeds slowly in cold water. Bacteria that break down organic matter work less efficiently at low temperatures. A dead fish may lie on the seafloor for months, gradually losing mass, tissues softening, eventually collapsing into a skeleton. Scavengers accelerate the process. Amphipods gather on carcasses. They consume soft tissue. Sea stars feed as well. But even with scavengers, decay is protracted. The nutrients locked in the body are released gradually. They re-enter the water column. They become available to bacteria, to filter feeders, to the base of the food web. Nothing is wasted. Every molecule is recycled. The system is closed enough that efficiency matters. The underside of the ice shelf is not a flat surface. It has features. Valleys carved by flowing meltwater. Ridges where ice has refrozen. Smooth areas. Rough areas. These features affect water flow. A valley channels current. A ridge disrupts it. Organisms respond to these features. They may shelter in valleys. They may avoid ridges where flow is turbulent. The topography of the ceiling shapes the environment below. But the topography is always changing. The ice flows. What was a valley yesterday is elsewhere today. Organisms cannot rely on the ceiling as a stable landmark. They must adapt to a roof that shifts. The water beneath the ice came from the open ocean, but it is no longer the same water. It has been transformed by its journey, cooled by contact with ice, diluted by meltwater, stripped of oxygen by respiration, enriched with nutrients from the seafloor. The longer water remains in the cavity, the more it changes. Near the ice front, the water resembles ocean water. Deep within the cavity, kilometers from the edge, the water is different. It has become something unique. A hybrid, neither fully ocean nor fully meltwater. The organisms here live in this hybrid environment. They do not know the open ocean. They only know this transformed water. The seafloor is covered in fine sediment, silts and clays. The particles are so small they remain suspended if disturbed. They settle only in stillness. The sediment is soft. An object placed on it sinks slightly. Organisms walking across it leave tracks. But the tracks do not last. The sediment smooths over time. Grains shift microscopically. The surface heals itself. Beneath the surface layer, the sediment is compacted. It has weight pressing down from above. It has lost most of its water. It becomes firmer with depth. At some point, it transitions from sediment to sedimentary rock. But that transition is far below, meters or tens of meters down. The organisms interact only with the surface. The world beneath is inaccessible. The cavity is not silent. Sound is present. The crackle of ice melting. Tiny bubbles forming and collapsing. The hum of current moving past obstacles. The click of a shrimp's claw. The low-frequency vibrations of distant icebergs calving. These sounds travel far in water. They reflect from the ice above and the seafloor below. They create an acoustic environment. Organisms use sound to detect prey, to avoid predators, to navigate. But the sounds are not loud. They are subtle. The soundscape is quiet compared to a coral reef or coastal shallows. It is a murmur rather than a roar. The organisms here are contained. The ice above is impermeable. The seafloor below is solid. The only exit is lateral, toward the ice front, kilometers or tens of kilometers away. For most organisms, that distance is impossible. They lack the mobility. They lack the energy. They are born in the cavity. They live in the cavity. They die in the cavity. Their entire existence unfolds in this enclosed space. The cavity is not a habitat they chose. It is the only habitat they have. There are moments when the water does not move, when currents pause between cycles, when nothing swims, when nothing feeds. In these moments, the cavity approaches perfect stillness. Particles suspended in the water column hang without drifting. Sediment on the seafloor remains undisturbed. The only motion is molecular. Atoms vibrating, molecules colliding. But at the scale of organisms, there is no movement. The stillness is not temporary. It persists for hours, sometimes days. Then, almost imperceptibly, flow resumes. The cavity exists whether observed or not. The organisms continue their lives in darkness regardless of human knowledge. The ice melts. The currents flow. The bacteria metabolize. Observation does not change these processes. It only reveals them briefly. The vast majority of the time, the cavity is unobserved, unexplored, unknown. It operates according to physical and biological laws. Without audience, without witness. In the open ocean, time can be marked by sunlight. Dawn, noon, dusk, night. The cycle repeats. Beneath the ice shelf, there is no such cycle. Time passes uniformly. Hour after hour. Month after month. Year after year. Without differentiation. An organism living here for 10 years experiences 10 years of sameness. Not 10 years of seasons. Just 10 years. Water holds properties that reflect its history. Temperature records where it has been. Salinity records what it has mixed with. Dissolved gases record when it last contacted the atmosphere. The water beneath ice shelves carries these memories. Some water has been isolated for decades. It remembers a time before recent changes, before the grounding line retreated, before melt rates increased. That water is a link to the past, but it is a fading link. As it mixes with new water, the memory dilutes. Eventually, it is lost. Life here progresses in increments too small to notice. A sponge adds a microscopic layer of tissue. A worm advances a fraction of a millimeter through sediment. A bacterium divides into two. These increments accumulate over vast timescales. What appears static is actually slowly changing. But the change is so gradual that it defies perception. Only by comparing states separated by years or decades does the change become visible. How many species live in these cavities? The question has no answer yet. Each expedition discovers organisms previously unknown. The catalog remains incomplete. How long can organisms survive if the cavity becomes more isolated? It depends on factors that are not fully understood. Some species might persist indefinitely. Others might decline. The predictions are uncertain. What will happen if ice shelves collapse? The cavity will flood with light and warmer water. The organisms adapted to darkness and cold will face conditions they cannot tolerate. Some may migrate to remaining ice-covered areas. Others will perish. The outcome is not certain, but the direction is clear. The cavity is not the deepest part of the ocean, but it feels deeper than depth. It is not the darkness that creates this feeling. It is the separation, the removal from anything familiar. The ocean at 5,000 meters is deep, but it connects to the surface. Water circulates. Particles sink from above. The connection exists. Beneath an ice shelf, the connection is severed. The cavity is cut off. It exists in its own realm, not measured by meters below the surface, but by degrees of isolation. The ice has existed for thousands of years. It has witnessed changes humans have not recorded. Periods when the ocean beneath was warmer. Periods when it was colder. Times when the cavity extended farther inland. Times when it was smaller. The ice records these changes in its layers. But the record is being lost. The oldest ice melts first. The history it contains dissolves into water. Future generations will not be able to read what the ice once knew. There is no destination here. No goal toward which the cavity moves. It simply exists. Conditions shift. Organisms adapt or do not. The system continues. There is no climax. No resolution. Only ongoing processes. Some accelerating. Some slowing. All interacting in ways that produce no final state. Cold is not merely absence of heat. It is a condition with its own properties. Cold makes water denser. Cold slows chemical reactions. Cold reduces metabolic rates. Cold preserves. The cavity is defined by cold. Remove the cold, and the cavity ceases to be what it is. The organisms would not survive. The ice would not persist. The isolation would break. Cold is not a problem to be solved. It is the foundation of everything here. The sounds of the cavity are brief. The crackle of melting ice. The movement of current. The activity of organisms. These sounds occur. Then they fade. Silence returns. The silence is not empty. It is full of potential. The next sound will come. But until it does, there is only silence. The organisms here do not have a sense of history. They do not remember when conditions were different. They exist in the present. Their adaptations reflect the past, but they do not carry memory of it. Each generation inherits the genetic material shaped by previous conditions. But the experience is not passed down. Each fish swims as if the cold has always been. Each bacterium metabolizes as if the darkness is eternal. They are not wrong. For them, it is eternal. The cavity will not exist forever. Ice shelves are transient on geological timescales. They advance. They retreat. They collapse and reform. Thousands of years from now, this cavity may be gone. Or it may be larger. Or transformed into something different. The organisms will change as well. Some lineages will continue. Others will end. New species will emerge. The specific assemblage of life present today will not persist. But life itself will likely continue. In some form. Somewhere beneath the ice. The cavity is a boundary. Not a place with clear edges. But a transition. Between frozen and liquid. Between isolated and connected. Between known and unknown. Boundaries are not fixed. They shift. They blur. What lies on one side can move to the other. The cavity occupies this liminal space. It is neither fully part of the ocean nor fully separate. It is the space where these states meet. This is not an ending. The cavity continues. The processes described are ongoing. The ice melts and refreezes. The water flows. The organisms live and die. None of this stops because observation stops. The cavity does not require comprehension to exist. It exists regardless. Beneath the ice. In the cold. In the dark. This is only one of many hidden environments shaped by isolation. Beneath Antarctica's ice, others exist that remain sealed away. In the next film, the journey continues toward the lakes hidden beneath Antarctica's ice. A world separated from the surface for far longer than the ocean below the shelves. The underside of the ice shelf extends beyond sight. The seafloor stretches beyond measurement. Between them, water holds what it has always held. Life in forms adapted to conditions that permit no alternative. The cavity breathes, not with rhythm that can be counted, but with movement that persists. Water enters. Water leaves. The exchange continues. Somewhere in the darkness, a fish drifts. Its fins spread. Its body still. It waits for what the current might bring. It does not wait with anticipation. It simply exists in the waiting. This is the nature of life here. Not striving. Not declining. Simply present. In the cold water. Beneath the ice. Where the ocean transforms into something other than itself, yet remains the ocean still.